rang me up and said, would I like to come and give a presentation, and what would I like to talk about? And so I've been retired for nearly 20 years from Network Rail, and therefore it won't be very much about what's going on today. What we're going to do is look back at elements of my career and my involvement with track geometry and tamping machines. I'm a Geordie and proud of it, and happier to say that today than I was on Sunday morning. Being brought up in Newcastle, taken by my father to the Keep, from where this photograph was taken, you could argue there was a choice between being a mechanical engineer and playing trains, or being a railway civil engineer and trying to sort out the East End diamonds, which were probably world famous until Network Rail decided to simplify them. At 17 in 1963, I had an interview with the chief civil engineer of the northeastern region of British Railways in this building. This is the old station at York, still used, beautifully refurbished by York City Council. And I was offered a position as a student civil engineer, which meant that I would start a career to become a railway civil engineer. And I'm going to talk about track geometry and tamping machines. So, feeling that there may be one or two people in the audience who are not quite as familiar as most of us in the permanent way institution, I want just to explain how simple track can be, or should be. If we are designing a new railway, our track is made up predominantly of straight track and curved track. And then we have to join the two bits together in what's known as a transition, a length of track with varying radius from 0 to the radius of the main curve. Now clearly track is more complex than that, but if we can try and keep it simple, it's easier to install and it's easier to maintain. But those are quite important principles that we'll look at during the course of the presentation. So what is track and what does it look like? Well, no, it's not often you see track like this. This photograph is not from the UK, it's from Austria, but it shows quite clearly the different components of railway track. And I regard railway track as being a system, and I include all those bits that Network Rail don't include when they talk about track engineers today. As a railway civil engineer, I manage the system. So we start off with formation, that's Mother Earth. And for many railways, they have put a blanket of material here as basically a protection to transmit the forces and reduce the level of forces that go into what could be very soft ground. And at the bottom of which, here we see a membrane, which is the bottom layer of drainage. Drainage is probably the most important thing to a track engineer, to be able to get rid of the water that falls like it does today. The ballast, the sleepers, the fastenings, which are very important, which is the interface between the hard steel rail and the hard concrete sleeper, which needs a degree of elasticity, and finally the rails themselves. So that is our track system, and if all our track was like that, track engineers would almost be out of a job. Now we want to understand a little bit about tamping. What is tamping and how does it work? So I'll leave you to watch this short video for the next minute.
claim on that.
The very first tamping machines that came into the country from Switzerland and later from Austria were quite rudimentary machines. They were nothing more than the tamping bank you saw in the video attached to a frame. There were no lifting and lining systems. It was purely the means of putting some tines in the ballast and compacting the ballast. This photograph is from 1958-59, and it's the Placer depot when it was at Northampton, and some of the first machines that were brought in from Austria by British Rail. So here's our tamping machine at work, and again you can see from the photograph we're still in the early 60s. And as I said, there's no lining system, there's no levelling system, so we've got track jacks that the P-way gang has put in to put the track to the level they wanted at, and then this machine will come in and compact the ballast. These are the very early machines. I'm not sure if this is a BKR 04 or 05, but I do remember them because obviously they worked into the early 60s. And one of the very first lining machines in the very early days, correcting the alignment of track and correcting the vertical profile of track, or the top, were done by two separate machines. So this is one of the early lining machines, and it worked on the basis of having two cords. There was a cord that went from the front trolley to the rear trolley, 24 meters long, and a shorter cord that went from the front trolley to the center of the machine, some 12 meters long. And the way in which the machines worked, in fact, the way in which tamping machines worked, is based on an understanding of trigonometry and mathematics. So I mentioned this machine had two cords. If you imagine one cord is from X to Y on this diagram, and the second cord is from X to B, and we want to correct the first sign at point B, we move the track until we've got a relationship at point A between the short versine and the versine in the center of the curve. And that relationship mathematically, AF is 1/3 of AG. So if we know that, and we have a curve of a regular radius, we can use this formula to regularize the versines and to regularize the radius. And on that principle, modern machines today rely upon that. But the tamping machine with lining cords is very, very similar. We're working from good track towards poor track, and we want to bring the poor track up to the level of the good track at the back. So we need to raise the cord between the front tower and the rear tower, measure it at the point at which we're going to compact the track, and as we lift it with clamps to the point where we've got a straight cord line, we know that's the point at which we want to then compact the ballast. So again, this principle too exists on modern machines. But in the very early days, there were problems because we had no ability to have computers that told us what to do when we got to a transition between level track and track that rose with super elevation on transition curves. Nor did we have a system that told us what to do when we got for alignment at the end of a piece of straight track, and now we started to have an increased radius into the main curve. So mathematically, it was possible to produce adjustment values. So the operators on the machine had to take this chart with them, one for lift on the 07 machine, one for alignment. They had to know the radius of the curve they were working in and read off to the value of cant a number on the chart to adjust the level on that front tower to make sure that they didn't start ramping up track into fresh air. So in the early days, it was quite a skill to be able to manage these machines. And most of British Rail's recruitment, I seem to recall, was from lengthmen, from people who worked in the length gangs. And they were put in through a training course, and I'm sure there must have been a few who perhaps didn't get through the mathematics. But things changed very quickly, and the next series of machines, this is an 0632 machine. 06 is basically the sequence of numbers of development of machines. 32 is the number of tamping times that are going into the ballast. So if we've got 32, that means it's a machine that's tamping 2 sleepers at once. So this is a very popular machine because it had the ability to level the track. So we've got an operator here in what's called the front tower. He was setting up alignment, not by cords in this case, but by lights, into the main machine. These points here. And that's allowing the position of this rail to be corrected. This is a track renewal. You can see that in the front, our track is low and it's not level. But to the back, we've now got the correct track position. In terms of providing information, how does the operator know how much to lift the track? Well, that was a job of technical staff who would go out and survey the renewal. Most renewals of plain line were done on a like-for-like basis. So in other words, we know where the adjacent track is. We use that as a reference for the new track. So there would be every half chord, every 33 feet, there would be a value of lift to put on the new track to bring it to the level that was required. And it's that information that this operator is feeding into his tower at the front to get that chord line to the right level. We can see to the rear a lining machine. 2 separate processors. And I've now lost my slide.
That's interesting. Machines. The projector's still on.
Here we are. Here we are.
Okay.
So this is a colour photograph of that same black and white lining machine we had a few slides ago. And in this time, we're not using anything in the way of an automatic mode. We've got the machine operator who's using a gauge to correct the alignment he wants on the 6 foot. Again, every half chord. 2 separate machines. Well, it wasn't long before Placer and Tora and other manufacturers in the early 70s worked out how to combine the 2 operations into one. And this is an 0716 machine, probably one of the more significant developments of the design of tamping machines, because the track was starting to get heavier. We weren't relaying wooden sleepers anymore, we were putting in concrete sleepers. We were putting in continuous welded rail. So there was quite an amount of strength required to lift the track out of the ballast to be able to correct the geometry. So Placer had to design machines with quite a strong frame. This is a visit to Linz by the PWI from Manchester in 1978. And you can see here the large section of frame between the 2 bogies to enable the track to be lifted. The 07 machine was extremely successful. When the first machine came down to Fratton, when I was the permanent way engineer there in 1973, I was over the moon because at last we had a machine that I knew was going to do something to improve the quality of my track. And I was sufficiently enthusiastic to make sure that I would meet the operators when they were on a shift on my patch, because the operators needed to know 1 or 2 things to be able to do a good job. Am I working on straight track or curved track? Is the track marked up? It's absolutely critical that the machine operator knew if he was going to work into curved track, where the curve started, where the curve finished, and the rate at which the cant was increased from the start of the transition to the top of the transition. So if we have something like 3 inches of cant at the top of the transition, there would need to be a uniform spacing between the sleepers where the cant varied every 1/4 of an inch as we climbed up the transition. If you could give the operators that information, they would do a better job. And of course, these were people who were working for you as a permanent way maintenance engineer on a night shift, and you wouldn't perhaps normally see them. So to be able to go out and say, look, you're part of the big family, we're grateful for the work you do, was quite an important mission, I felt. The other thing that we started to do was to improve the quality of the longitudinal profile of track. The initial machines that we were using with their lining cords, if we put them into automatic mode to what was called smooth tamp, they didn't eliminate all of the faults in the track. That's because of the distance between the start and the finish of the cord on the machine and the lifting point being at about 1/5 of the distance. So you would only get 4/5 of the benefit for the machine. However, if you could produce some design information and input that into the machine, you would get a much improved quality of work, whether it was alignment by stringing curves and setting out slews, or whether it was the top profile of the track. And one of the things we used was an instrument called an optic, basically a surveyor's level, as you see in this diagram, and a target. And if we place the level on a high point, and we place the target on the high point, by moving the target towards the instrument, we would generate an understanding of the depression in the track. And every 4 sweepers, we could take a reading and mark up a lift. And this is how gradually we improve the quality of our track, by giving additional information into the machine. And something I learned in those very early days was the better the machine information, the better the quality of work. So here I am hard at work. In the late 1970s, all of the regions of British Rail in the civil engineering department had permanent way maintenance engineers. The last to go with permanent way maintenance engineers was the Midland in 1977. And having been down at Fratton, I moved up to Manchester, and this is me on the line up to Oldham, trying to improve some track quality. The instrument is not quite the same as the one you saw in the diagram. It's quite short. These instruments were purchased by the Chief Civil Engineer of the Midland region and issued to every permanent way maintenance engineer with the encouragement to get on and do the job. And of course, they were small, so they would fit in the back of the car, in the boot of the car. To understand more about track position, there was a need to measure it. And some of the first machines that we used to measure track geometry were these quaint vehicles built by Matisse in Switzerland.
I think yeah, there's a blackout button.
So a total of 13 vehicles were put around the network. They ran at 20 miles an hour, and they were purely mechanical. So the trolleys on the machine had feelers that came into a system of pens that produced, with ink, a trace that you could take off the machine. It wasn't long before, in 1970, we got into the world of computers. Not computers as we know today. The data was punched into ticker tape and sent to Nottingham to be processed. Nevertheless, we were able to turn graphical information into numerical information. And this was the first start of being able to understand the quality of our track by numbers. But things moved on, and Derby Research, British Rail's Derby Research in the 1970s, started to work on a system of measuring track by accelerometers fitted to the bogies of a coach, a normal passenger coach. And by 1978, the system had been proved, and the Chief Civil Engineer was grateful to accept into service the first high-speed track recording coach. The coach would take readings every 240 millimeters and produce track quality indices based on the roughness of the track. Now, clearly, there's a risk here that the vehicle is going to set up some dynamics itself that might affect the quality of the readings that were taken from the accelerometers. There was also a need to provide some filters, otherwise we were going to end up with valuable information and rubbish, which wasn't of any help. And the UIC, which is the European Association of Railways, got together and agreed that we ought to consider 35 and 70 metre wavelengths to be able to measure track quality. And the way this was done was to mathematically produce the standard deviation of the variations from pure track geometry. And of course, that's what we have today. It's been developed, but it's the same basic system that was started with this coach in 1978, the high-speed track recording coach. You now know it probably as the yellow machine or the new measurement train, exactly the same system. Another development that took place as we understood how our track geometry was the management of ballast being installed in track renewals. We were doing a lot of work with optics, trying to get smooth track. Sometimes we got the smooth track, and then 3 weeks later it went back to where it had been. Derby Research was starting to do some work to understand why this might be, and they came up with the concept of ballast memory. But they then said that through research, the shape of the profile, the longitudinal shape of the profile of the rail seemed to match the profile of the interface between the ballast and Mother Earth. So back in 1985, when I was the Divisional Civil Engineer at Nottingham, one of the young lads came to me, he's called David Ratledge, by the way, and said, "Boss, I've got a brilliant idea. Can we use a beacon laser to try and control the machines?" And of course, that system now has developed such that the beacon lasers on machines today read from a point cloud in 3 dimensions. So some very early days trying to improve track quality. The other thing that was happening was that the track we were producing in our maintenance using lining machines and the 07 machine wasn't quite as good as it could have been. There were no computers. It was all based on either input data or a best judgment on the night. And so Derby Research were asked to come up with a solution to try and create a system of automatic track alignment, which they did. It was called ATA, and it was fitted to the first machine in 1988 for trials. It was a success, and by 1993 we had 30 machines fitted, purely working on alignment. It was then thought, well, if we can do it for alignment, why can't we do it for the longitudinal profile for the top? And so the system was developed, and that became known as ATTA, some of you may remember. And it was fitted to a new machine, a number of machines. Meanwhile, in Linz, Placer and Tora were developing their own system, known as ALC, and that was introduced in 1990. It was a PC-DOS system based on an IBM computer. Some of you may remember the concept of DOS. I didn't try and learn it at the time, but I was delighted when Windows came along, as were Placer and Tora, because by 1996, they had the first Windows ALC system based on Windows 95, and Placer at West Ealing started to install that on a number of the 07 machines. And that gave us the ability to improve the quality of work, because we were able to work out how to improve long wave faults on our high speed lines. I worked on the West Coast Main Line in the 1980s. Strengthening continuous welded rail fitted with BJB fastenings for the ill-fated advanced passenger train. And also managing lots of broken rail problems as a consequence of the AO6 electric locomotives, which everybody knew were not fit to be run at 110 miles an hour, but still run at that speed. It was an interesting 4 years. I moved on and didn't expect to come back. But of course, that's not the way it works in a railway career, is it? So I want to talk a little bit about West Coast route modernisation. Time. Okay, good. If you're interested in a little bit of history, it's worth looking at some of the documentation about this project, which in the end resulted in the demise of Railtrack, and to a certain extent the success of Virgin Trains. It was set up as a joint venture between Virgin Trains and Railtrack to create in-cab signalling and run trains at 140 miles an hour from London Euston to Glasgow. Well, that really was thought as a pipe dream by some of us at the time, and it proved to be. The West Coast was only running at 110 miles an hour in 1998. We had 125s running successfully on the East Coast and Great Western, and there was a need to do something. So when the Virgin decided they were going to go with tilting trains, taking a leaf out of BR's book from the late 1970s, we had to decide in Railtrack how we were going to manage that and cope with it. Well, we started off when I was the controller of Railway Group Standards in Railtrack Safety and Standards Directorate, which is currently is our SSB. And we needed to write some standards for the track and for the train. So with a colleague from operations, we went and visited the Italian railways and the Swiss railways to find out what they were doing. And after quite a lot of work, through others, not myself, we came up with the concept of some changed rules on curving. Now, when trains go around curves, they do so smoothly, principally because of passenger comfort. They don't go around at curves usually for a safety reason. The speed at which trains go around curves has got safety well in hand, unless, of course, you tilt. If you tilt, your passenger comfort is cared for by the tilting mechanism of the train. So we had to think very carefully as railway civil engineers about our new curving rules. How quickly could we take a train and twist it up a curve, a bit like a roller coaster at a fun fair? And what we were going to do about cant efficiency, in other words, how much lateral force could we allow the bogies to take into the track, which obviously wouldn't be felt as a centrifugal force by the passenger in the train. So having set some rules, we also knew we had to do some realignment work. The West Coast has got a lot of very short transitions which limit speed. So we allowed the designer to smooth track up to 75 millimeters. We were not building a brand new railway, we were refurbishing an existing railway and trying to run existing traffic at the same time. We had a concern about clearances should the tilt mechanism fail. The West Coast Main Line runs, as most dual track railways do in the UK, with a standard 6 foot. And if the tilt mechanism failed when it was fully tilted at 9 degrees, and another train coming the other way had got the same misfortune, the two would hit. So we had to minimize that risk, both from the mechanical engineering side and the design of the tilt mechanism, but also from the track perspective. We had to make sure that our track was always going to be in the position we put it in. So we came up with the concept of absolute geometry. I'll tell you a little bit about how we did that in a moment. As well as going to Switzerland and Italy to look at standards, I went again in 2002 after I'd been brought into the West Coast team to look at how they maintained their track. We also went to visit CTRL, High Speed 1. It was being built in 2002 in Kent, and it was being built to the French standard for their TGV routes with ballasted track running trains at 180 miles an hour. This is a slide from Sistra, the French consultancy. This is the cross-section of the track and how it was built on High Speed 1. And what it shows is the track's ballasted speed. This bottom line is the top of formation. And the formation is basically a pavement with a consistent bearing capacity. Onto the pavement was put ballast. Sorry, onto the pavement was put the track, French track, duo block. And then ballast was unloaded and the track was lifted up through the ballast. And the ballast was put in layers. Not only was the ballast put in layers and the track tamped, but also there was stabilisation taking place with dynamic track stabiliser twice in the process to achieve 350 millimetres of ballast. So we certainly took that away in terms of the quality control we would need on our track renewals. Track is maintained in two principal methods. By machine, we have what's called reference geometry, and we have absolute geometry. Reference geometry means that you're maintaining your track purely by reference to its current position. We'll respect the start of a transition, the end of a transition. We'll respect the fact that there's a structure, which means we can't slew the track more than a certain amount, or maybe not at all. But broadly speaking, as we do track maintenance by reference, we're creating a new design. And when we've done that work, and we come back 2 years later, or maybe less, we repeat the process, and we create another new design. And British rail standards, network rail standards allow that to happen up to 25 millimetres of slew and lift without a redesign. Absolute geometry is by reference to the original design alignment position. Absolute geometry means that you put your track in an absolute position and you're going to keep it there as best you can. And you'll do that by referencing the track position to fixed points down the side of the line through a geometry survey. And when you want to maintain it, you carry out another geometry survey to find out where your track is in relation to where you think it should be. You find it's moved, and therefore you create a correction file in the tamping machine to return it to its original design position. So in the visits I made to Austria and Switzerland, I learned that the Austrians and the Swiss apply absolute geometry to all of their track maintenance. There is no reference geometry. In Germany, it's about 75%. Interestingly, at the time I went, the French were maintaining their TGV network by reference geometry. It wasn't something I knew at the time, but I learned about that later when I discovered they suddenly got into a system of absolute geometry. Sorry, I should have said with this slide, this is Switzerland and this is a Matisse tamping machine using an absolute geometry guiding system called Pallas. And you'll notice the gentleman taking a measurement, and you can just see on the platform slide, the red dot is a fixed point. And that fixed point holds the XYZ coordinates of the track position. And he's carrying out a check of the horizontal dimension to that fixed point with a Mephisto surveying instrument. In Austria, where I visited, OBB several times. All of their track is maintained by absolute geometry. Not only that, the interesting thing about maintenance tamping in Austria is that in the files held on every tamping machine are the absolute geometry files for the track geometry for the routes on which they work. This is an MSAT machine which uses a long chord survey to establish the track geometry that needs to be adjusted for absolute track geometry maintenance. We'll come back to this in a couple of minutes. In the meantime, we were busy renewing track on the West Coast Main Line. The original concept had been to renew all the fast lines from London to Glasgow. That not only proved to be far too expensive, but it also proved to be going to take too long. It wouldn't be till 2013, some 12 years later, that the work would finish. So that was unacceptable, the cost was unacceptable, so a compromise had to be made. So in the end, we only renewed that which we needed to renew to be able to operate the Pendolinos for the first 2 or 3 years with our higher track forces. And the mainstay of the work we did on track renewals was the 07 machine. British Rail had had the foresight, with privatisation being on the horizon in 1994, to get many of the 07 machines refurbished by Placer and Tora. So these machines came out of Placer's into the early years of privatisation, allocated to track renewal companies with fully operational onboard Windows ALC guiding systems. The other key tool we used, think back to my slide from Sistra of the Channel Tunnel track, Channel Tunnel HS1 track, stabilisation. This is a dynamic track stabiliser, one of, I think, 15 independent machines bought by British Rail in the late 1970s. And they were used to be able to renew track and open it at 125 miles an hour at 4 o'clock on Monday morning. Sadly, although we made good use of these machines, in fact, 4 of them went back into Placer's to be totally refurbished, because by 2000, 2001, I think there was 1 with Carillion and there were 4 with Jarvis. Their measuring systems had been basically ripped out. They were used as track thumpers. But we changed all that because we wanted to measure what we were doing. So when they went in to be refurbished at Placer and Tora's, they were also refitted with their data acquisition recorders, which proved quite crucial. So what does a dynamic track stabilizer do, and how does it work? I'm pressing too hard.
I think you just catch, there's a blackout button on that, you just catch in the corner of it.
Okay, thank you. So here we see the working part of a dynamic track stabilizer. In the previous slide, it's painted white. It has a rotating shaft, which has an eccentric cam on it, which vibrates the trolley horizontally. We've got clamps that fit on the rails, so we're now shaking our track from side to side. We're doing so at a set frequency, the same frequency that we do our tamping at, 35 Hertz, although that could be varied a little bit depending upon ballast conditions. And then we apply a vertical load. The vertical load is applied by 4 hydraulic rams. On the independent machines, that vertical load was fixed. Nevertheless, by applying the vertical load, what we're doing is we're impacting the first 100 millimeters of ballast underneath the sleepers. And they're all vibrating from side to side. They're moving about and they're locking due to the vertical pressure on their sharp edges and creating a solid ballast grid. And the track is settling. It was said in the day that 1 pass of a dynamic track stabilizer was equivalent to about 2 weeks of traffic on a main line. And if you think about the early days of track renewal, when we had speed restrictions for 2 weeks until we raised the speed to line speed, That's how this dynamic track stabilizer can eliminate that need and go straight from new track to 125 miles an hour in a single shift. These were invaluable machines to the work we were doing on track renewals on West Coast. Initially, we were putting track to a new like-for-like position. And then once we had our through alignment design proven for 125 miles an hour, we came along and moved the track to its new design alignment position and registered it to fixed points. We copied another system from Austria, which had been used before in the UK. Andrew McNaughton used it when he was the the divisional engineer at Newcastle. We're working 3 machines as one. We've got a tamping machine, in the middle we've got a ballast regulator, and behind it we've got the dynamic track stabilizer. It was very important that that dynamic track stabilizer was the last machine. And we would measure the trace from the dynamic track stabilizer, and providing there was settlement of the sleepers by no more than 2 millimeters, that was the job done. We also were lucky enough to have one of the new machines in 2002. And this is another development by Placer and Torre, to be able to tamp 3 sleepers at once in a continuous motion. So this middle portion of the machine in grey is a satellite that's moving backwards and forwards in synchronization with the machine that's slowly going forwards at about 2 or 3 miles per hour. This machine also came into the UK with the latest version of Placer's guiding system, Windows ALC. And when we were doing our track renewals, we had to meet the construction standard. And there were a lot of people in the Alliance at the time who said, oh, can't do that, it's too difficult. Well, I, for one, was determined to prove them wrong. The difficulty was that after we renewed the track, we had to wait sometimes 2 or 3 weeks before the new measurement train came down to demonstrate that the standard deviations were all green. They were all in the very, very good category. So I said to Placer and Torre, can you put a similar system on WinALC so that when we do a measuring run with a tamping machine, we can get standard deviation values? They took up the challenge, and it was with this machine that we did some trials to get approval of that software, and we compared the same piece of track, measuring standard deviations with the Placer ALC computer and with the new measurement train. David Ventry was the track engineer at the time, and he said, if you can do it 4 times in a row, Richard, I'll give you a tick in the box. And we got the tick in the box. And of course, that's now standard on all machines that are used on network rails infrastructure. And it's a key measure that they use when they do maintenance tamping. Have we got the SDs in the right value? Something else we tried to do with our track renewals was to put the track in the right position before we put the top stone in. So if we could get the supporting ballast profiled to the right profile with only a 25 millimeter lift or a 25 millimeter slew max reliant on the tamping machine, it made life an awful lot easier and improved the quality of work. And that track's almost good to run trains on. We had about 2,500 switch and crossing units to look at on the West Coast Main Line. We couldn't renew them all. We didn't need to renew them all. So we, after inspecting every one, we put it into a category of just needs realignment, needs some refurbishment and realignment, or it needs renewal. And when we came to look at how we were going to move the track into our, and create the track into our through alignment design position, we had problems. And if you've got any experience of tamping crossovers with one machine will know But if you don't make use of the extended arm to lift your long bearers, and you don't have some cangos to be able to support the tines, because the tines can't go everywhere, you end up basically having a crossover sitting on stilts, which is not sustainable. So again, I went to Placer and Toyer and I said, is there any way you can develop a system whereby we can have two machines working in tandem? So we've got our two tracks here and we've got our long bearers. We want to be able to do a survey, put geometry files in the machines so that both machines can be operated as one, lifting and tamping the long bearers as one. So the way we set the system up was to use an umbilical, basically a piece of wire connecting the two computers, an umbilical cord. And one machine was the master with the operator in it. The other machine basically was the slave. Now that system worked extremely successfully when we had to go to places like Ledburn Junction, Bourne End Junction, and Stoke Junction, where the series of running crossovers from fast line to, hello Malcolm, we did it, didn't we? You and I, and Bourne End. Remember?
Yes.
It was quite a complex process to be able to do the survey work on both tracks and coordinate your surveys to make sure that you were sufficiently accurate to be able to lift the bearer the right amount on both sides to correct the geometry. So nowadays, this system is widely used by Network Rail. I think it's called parallel tamping. The machines don't necessarily have the umbilical cord, but Network Rail is trying very hard in the maintenance of its crossovers to ensure that the whole of the length of the long bearer is properly supported by tamped ballast. Now, anybody who's done any tamping will know that the biggest problem is the signal engineer who puts the cables in the way.
Yes.
And something I was quite determined to do was to try and get this good initial quality in the track that was being put into the West Coast. And I wanted to tamp every sleeper. So I went to Schwehag and bought some hollow sleepers. These are steel. They're the first that came into the country. They have exactly the same geometrical profile as a G44 sleeper. So we don't need to worry about this level being above or below its adjacent concrete sleeper. Nor do we need to worry about the width being different. They should both perform in a similar manner under traffic. And we've got plenty of space to put our cables in. I wasn't 100% successful, of course, because the signal engineer then started to change his system, and we had to put up with the detectors. Never mind. We tried. I said that initially we had our contractors relaying our track, not necessarily to the final through alignment design. And we had one section of track, which was the down fast between Atherstone and Rugby, that was going to be used to test the pendulum at 140 miles an hour. So we wanted to make sure we got that track in pretty good condition. And this is an example of the down fast standard deviation values before we applied the through alignment design, and then using our three machines as a single system, tamp regulate, dynamic track stabilize in maintenance, we achieved these values, which was very pleasing. There were lots of people who said, oh, it can't be done. Oh, yes, it can. In fact, we use this slide quite a lot to demonstrate that if only we could get the initial quality of our track to a high enough standard, then it should last for a number of years before it needed tamping. Whereas I think you find in BR days, in the 1980s, there was little track that wasn't tamped every 12 months. A lot of it was tamped every 6 or every 9 months.
Wow.
Surveying was a little bit of a free-for-all in 2000, 2001. There were a number of private surveying companies, all sort of doing their own thing. There were no standards for surveying on network rails infrastructure, on rail tracks infrastructure then. On West Coast, we contracted a Swiss company called Terra to come and do some surveying for us, because we thought it being the early days of satellite positioning and coordinate geometry, that there might be some success to be gained by using their trolleys. They started work in Switzerland with the concept of using trolleys, total stations, to do their surveying. And we certainly used the system very successfully. You can see the beacons picking up information from the satellites. There was a fair bit of work to be done on regression analysis, depending upon the time of day and where the satellites were. And it was early days. We had some success. I wouldn't say we had 100% success. And there's no doubt if you look today at the West Coast Main Line, the coordinate geometry south of Crewe is not as good as I would like it to be, because that was the bit that we learned on. Having learned a few mistakes, we applied those corrections to the work we did north of Crewe. So I guess the nearer you get to Glasgow, the more accurate the survey information was. Not quite, but you get my drift. This, of course, is now standard practice, as we'll see in a couple of slides. Long chord surveying. The Austrians had perfected long chord surveying long before they got machines to do it for them. But this is a photograph of Austrian railways using their MSAT system of long chord surveying. And basically, in absolute geometry, we've got outside the railway a grid of ground markers. We come into the railway, and we've got a grid of points on our overhead line masts. And then we've got our through alignment design, our string line of geometry for our track position. They're all fitted together as a single system. And what we're trying to do here is project a laser beam along the track. We know its position here, we know its position there. We can relate it to the datum rail, and taking offsets to understand the position of the track, both in terms of its height and its lateral position. This seemed an excellent system, and it gave the accuracy that certainly I was looking for, 1 millimeter accuracy. And the way in which the system works is that we start up at the top. F1, F2, F3, etc. are our fixed points. We start out with our MSAT measuring system here. We send out the satellite, and then the machine walks down the laser cord. And as the machine walks down the laser cord, every 200 millimeters, it takes a measurement. Those measurements will then be translated into a tamping file. When the tamping file goes into the tamping machine, it's using information that's been corrected every 200 millimeters. Nobody's having to interpolate between two different half chords. It's almost a consistent source of data, putting the track in the right position. This is one of the machines we brought in from Austria, working on the West Coast Main Line. This is the machine that's used to measure the horizontal distance to the fixed point, and our laser receiver is here, and this is the equipment underneath the machine. It would have been nice if we could have had this system incorporated into a tamping machine. More of that in a few minutes. We use datum plates as our fixed points. And the little cross on the top of the datum plate is the fixed point. And with the sighting equipment that we had, we could accurately pinpoint the centre of that cross from the track to record the horizontal and vertical position, and also to note its longitudinal position, because we needed in coordinate geometry to know where you are horizontally, vertically, and longitudinally. Now that longitudinal measurement gave us a little bit of a problem with coordinate geometry, because we had to remember the Earth is round and compensate for it. This was the instrument that we used for the lateral measurements, a Mephisto. And as part of the maintenance regime that was established once we ran Pendolinos from September 2004 to Manchester, the track maintenance engineers were all given these machines to be able to measure track position. You could have perfect geometry, but the whole thing could move. So you had to put it back. It didn't happen, but theoretically it was possible. We did a lot of training. One or two familiar faces to one or two here. We went out to Germany, to a company called DGT, and we set up an arrangement for a 1-week training course on how to use the MSAT and measure track geometry. It's great fun. And this is a classic photograph of the Pendolino on the west coast. And don't look at the train, look at the track. That's how we wanted our track to be.
Does look good. Good. Yes.
And I want to come a little bit up to date with what I regard as being some of the success stories of today. So the last couple of slides. High Speed 1. High Speed 1 measure their track geometry with the new measurement train. Sounds good. That's what it produces. That's no good to man nor beast. Because high-speed railways have got very long, flat curves. They've got very good track geometry. So what the engineers on High Speed 1 have to do is say, okay, thank you, Derby. They then put it through an enhancing system with a German company so that they can actually see in more detail what's going on. It almost becomes an argument for changing the filter for high-speed trains so you've got 140-meter curves, chords rather than the 70. We saw some of the early Swiss trolleys. This is now standard practice, I think, in nearly all of the alliances renewing track for Network Rail. Whether it's the Amberg system or the Trimble-Guido system. What's amazing about these systems today is they don't just measure track position and track geometry. They incorporate the design of the track. At the press of a button, they produce lift and slew files for tamping machines. The world really has moved on. I just wish they were used for maintenance.
Yeah.
Tamping machines have changed too. State of the art 09 4x4. Designed specifically to cater for the way in which Network Rail wants to allocate its machines to work sites. Just as good in a switch and crossing layout as it is on plain line track. We no longer have the use of the large 3-sleeper tamping machine for maintenance work. But this machine's got something else. It's got a system down here called curved laser, which is basically a very similar system to the MSAT. So anybody today who wants to engage in absolute geometry or manage track position can make use of this machine and its geometry surveying system to be able to improve the maintenance of that track. So some final thoughts, just my last slide, and I've hinted at it already. Why is there such a big gap, in my view, in the quality and accuracy of track geometry data for track renewals, which is brilliant, And for maintenance, well, basically, we just say to the tamper, go and measure it and do the best you can. And having done the work, why is there still such a big gap in the quality and accuracy of the way in which we measure our track, having done a track renewal, which is brilliant. We're as good as anybody else in the world in the way in which we measure what we've done, and we create as-built files. But for maintenance, we just look at a standard deviation and make sure there's no twist. There is a European norm, which is a British Standards publication now, called EN 13231, published in 2013. And it specifies the acceptance of permanent way work into maintenance after renewal work, which Network Rail follows pretty well, and after maintenance work, which Network Rail, I'm afraid, does not. I hope you found it interesting and enjoyable. I'm sorry if I've not left a lot of time for questions. Maybe that was my plan all along. Some references I've used to put this presentation together, because it's not all in my head. Just an example, that textbooks on track, published in 1994, the laws of physics don't change. It's still a valuable book to read today. The PWI journal. If you were, I'm not sure how easy it is to access archives, but there were some very good technical articles written, 2003, 4, 5, 6, 7, 8, 9, 10, about the work I've described very loosely tonight. I hope you found it interesting. I hope I haven't sent you all to sleep. Thank you very much.
Richard, thank you very much.
Should I attempt to put more? Put the bottom screen right.
Never trust a civil engineer.
Yeah.
Okay. Thank you, Richard. That was very interesting. I now understand the topic. Right. Is there anyone who's got any questions they would like to answer this?
I've got a few comments online. That's where I want to fit them in. So,
well, let's start with the room, Mick. Yeah.
Thank you very much. Made a very compelling case for dynamic track stabilisation. So why did it fall out of favour?
I wish I knew.
It did, of course, have a little bit of a comeback
When it was fitted into the high output ballast leading system, system 4, I think, and it was an integrated part of the system. Also, a lot of good work was done in Network Rail using dynamic track stabilizers on switch and crossing layouts, something which we actually had a go at way back in 2003. I think it is becoming more accepted now. It's an essential prerequisite on high-speed 1. So I think, like a lot of things, Mike, there's got to be somebody who's got some enthusiasm to say, I'm going to have a go at that and make it work. And that was the spirit that I certainly had as a young permanent way maintenance engineer. You know, a lap bed was a challenge to get rid of. So I hope that it's not dead and buried, certainly. And of course, all the modern machines, the 09 4x4s, have got integrated DTS. And the new DTS system has got advantages over the independent machines because you can vary the vertical load. It's more user-friendly.
Phil, do you want to ask somebody from remotely if they want to ask their questions?
okay, so the first one was Gary Smith. He's got 2 comments on the chat. First of all, he just said Hounslow Junction. He did actually put that in the chat while you had it on screen. But
that's exactly. It was the first one done under maintenance. It was the first one done by the maintenance team.
Awesome.
Bank holiday weekend, and it rained.
Brilliant. And his second comment from Gary again, he says they use the Amberg IMS 3000/5000 for maintenance on L&W South to create designs for ATG management.
Yeah. That's right, yeah. I should have mentioned that the West Coast is the only part of Network Rail's infrastructure where geometry files are prepared for tamping machines. The rest of it's all done by pre-measurement. Oh, and HS1, of course.
Awesome. Right.
Okay, John,
Gary,
hang on. Just
you,
go for
you
something.
happy with that? Do you want to add anything more? Or?
No, that is everything. No, I must have misheard. Well, that was all. That was because I thought you said that we aren't using the Amberg or the Trimble in maintenance. That's why I added that comment in there. So that was it.
Only on West Coast because they have to. I'd like to think it was used elsewhere voluntarily because somebody wants to improve the quality of their track.
Go on.
The first geometry file for a temper on the West Coast Main Line was about 1985. The Dutch system for the driver. We had one machine converted, and we were using a long laser cord around the curves. The big problem was doing the survey for it because we were trying to survey the masts for the fixed points, and getting enough sightings was damn near impossible with a total station machine. Theodolite set up in the CEST. And we had one section at King's Langley done for it. The biggest problem with that was transmitting the data back to Holland through modems when you couldn't convert, when you tried to take a Dutch modem input into a UK phone. Plus you had the problem with the person, the Grove didn't like us using international calls for about 2 hours transmitting the data about a kilometre of track.
But I think if you went to do that today, it would be so much easier.
It would be.
Because the systems are there to make it so much easier.
So it was being done in the early 80s, but I then left and went to be on that same patch and never saw the system again.
Do you want to try the? Is there anyone else?
Yeah, there's more comments online. Yeah. So the next one is just a comment. It's not a question. Comment from Thomas Dalton mentions that the Trimble Guido IMS surveying devices are now being used for maintenance on Western Route.
Brilliant.
Please out.
Brilliant. Thank
Well, it might make you happy.
Shoot me down in flames. Absolutely brilliant.
Brilliant.
More
Right.
sense to your elbow.
And if I can carry on from
Yeah,
online.
yeah, go on.
So on to hello, he's just Thomas has just come up again. Also using overlift and DTS regularly on Western, he says.
Yeah.
To make you happy.
I mean, I didn't go into too much detail about the principle of doing overlift or even maybe using a sprinter tamper. There are techniques that have been developed. There is some very, very good work done on Western. And may I mention Graham Penfold, who has been extremely supportive of using dynamic track stabilizers. In fact, he's written a paper on the subject.
Awesome.
Anything else on the one? Go on, one more.
Yeah, so one more from this is from Phil Ransom. He says a comment and a question. Phil, if you want to turn yourself on and say this yourself, if not, I'll read it out for you. It's up to you. So he says comment.
You can. I'll read it. I'll read it out. But I'm not sure the sound's particularly good. I don't know if you can hear me. Okay, I've got a fairly poor internet connection.
We can hear you perfectly. Don't worry. Far away.
Okay. Well, anyway, I'd just like to thank Richard for an excellent presentation. Obviously, he's run through the whole history there of mechanised geometry maintenance, surveying, and track installation. I'm proud to say I've worked with him on some of those elements, but at the end of the day, he's driven some significant changes in the industry, which I think we should all welcome. And an excellent presentation. Basically, should be a required learning, I think, for any track engineer, young or old. And I've really enjoyed it. Thank you. I am going to ask a question. I think, Richard, you mentioned that Dave Ratledge was once a young engineer. Is this true?
Oh, best question of the night. Question mark.
Well done. Thank you very much.
Okay, we'll go back to the room.
So Richard and I managed her for a number of years. So two things I'll bring up. Actually, my first day on the railway, Dave Ratley was on my left, and Melanie Denley, who she is now, was on my right. And what a baptism of fire that was. So first things about HS1. So I'm privileged to establish the first maintenance regime and bring the first tampers in. And we had to go with UK tampers, and they weren't man enough. So we actually hired ones in from France, the big material ones. But on the first phase of HS2, when we started to do that surveying, I said, so where's the design? And I was absolutely flabbergasted that the track was built to a very high standard, but wasn't monumented. And so then phase 2 was being built, and actually, so I worked for Carillion then. Carillion was actually putting the track in. But we managed to influence the monumenting of doing it, because once you've built a railway, especially a high-speed railway, you've got no access to, monumenting it in the dark is bonkers. So that's a bit of a surprise. But when you've got a railway where the tracks are so far apart, and anything that a train's going to hit, like a bridge abutment, is such a long way away, all the reasons perhaps for doing it on the sinuous west coast. That's the first thing.
I did offer Chris Jago a paper on the benefits MSAT would bring to HS1, but he wasn't interested.
So as far as measuring geometry on the HS1, so again, Carillion did set up a joint venture company with Stripbomb, and we introduced this machine, brand new from class at around 160 kilometres an hour. I was able to survey it once a fortnight, which, dare I say, in those days, Network Rail, the new measurement train was, well, it's an old HST that's got a lot of kit on it. It's probably parked out there. I mean, it's yesterday's talk, but there was a not invented here syndrome piece. And ironically, that machine's now working for SNCF. And it's, anyway, perhaps that'll be another chapter in my memoirs. But more seriously, it's about how do you sustainably introduce new techniques and technology. Just retired after quite a long career for one of the bigger engineering companies. And what distinguished us in the marketplace, we realised, was technical excellence. Now, Network Rail or Great British Rail, the big things, the passenger experience, trains on time, comfort and so on. But when you come down to an engineering level, surely the track engineers of the UK today and around the world should be so hungry to get this stuff. As we, we've got more computing power in your pocket in a mobile phone than we ever had on. Well, there's no computing power on some of those photographs.
No.
And the computer literacy of people is of a much higher order than when the new generation of tampers were brought in the late 90s. And ALC, one of the problems with ALC and ATA and all that is the guys haven't got a bloody clue with frightened of the computers. So I think it's a leadership piece that's required. We've got the competency generically, but we're actually going to put through alignment design as a way to do it and just catch up. We did it in this country with rail brakes after Hatfield. We were back. When I say we were back at the class, we didn't actually know about gauge contract. We knew we got it. We didn't know what to do with it. And now we are preeminent in the world in rail management, mixed traffic railways. So
I think to extend the West Coast concept of absolute geometry or managed track position, whatever you call it, it's about absolute coordinates. To extend that to other routes, you really need a project. Now, TransPennine are going to adopt a through alignment design, and they're going to have fixed points under Network Rail's managed track position concept. Managed track position is in a Network Rail standard, and for me it's got a flaw in as much as you start off with the geometry, the through alignment design, and the fixed points, but then in certain situations you don't follow the principle anymore, and you might come back to it 6 years later. It's got 3 levels, 0, 1 and 2. Managed track position level 2 is absolute track geometry. And that's being used on modern electrification projects where you have limited clearance for overhead catenary under bridges, and you have limited capacity to lift the track. So you haven't got the freedoms of plus or minus 25 millimetres when you do a maintenance tamp. You've got to put it back where it is. So that's another opportunity to learn the principles. But you really do need a project. I remember going to Andrew McNaughton and saying, look, why don't we put absolute geometry on the East Coast? He said, well, go and produce some estimates for the surveying necessary. And it was mind-blowing. You couldn't afford to do the surveys. But if you're doing new work, the survey comes as part of the package. So keep it and take advantage of the fact that somebody's done it for you.
I think there's a paradigm in there to be changed. It's difficult today.
We've got a hand on the thing. I don't know if that's a new question or what.
That's a new question, yeah.
Okay.
It is. Is it my hand by any chance?
Yeah.
It is indeed. Yeah,
Go ahead.
No, it's just a quick question regarding the failing of the 140 mile an hour Pendolino. Now, I heard a rumour as to why it was kiboshed, why it didn't go ahead and why it failed. But as you were there, what was the reason? Was it because of in-cab signalling?
No, it's because of level crossings. The ORR refused to allow trains to go faster than 125 miles an hour for as long as Network Rail still has level crossings.
Okay.
And that's the rule today.
Didn't know that.
Interesting. I thought that was due to in-cab signalling as well.
Well, the in-cab signalling is there. Well, it's sort of. It's latent. But there's a form of in-cab signalling that controls the tilting of the train. There are balloons all down the West Coast Main Line.
The irony is that the Pendolinos don't need to tilt to go at 125. That was a design feature for 140. So now it's just passenger comfort. And so it feels like you're in the
But that's, passenger comfort is quite important. If it wasn't for the bloody seats.
Maybe I should change that to passenger sensation. Not essential comfort.
Yeah.
Work is being done at the moment to look at the limits on curving all around acceptable sensations that passengers could accept, could take. It's all about passenger comfort.
Okay, happy with that?
Yeah, no, I'm happy. Thank you.
Sorry, there was a question at the back of the room. I cut away from you.
Yeah,
So.
sorry. Rich, you alluded to the cost of surveying and that it really needs a project for it. My gut feeling is we're not going to have a West Coast where you've got a project end to end anymore. So would the installation of control not be a bit bitty on somewhere like the East Coast Main Line, for instance, and you end up with a discontinuous grid such as the one you described, Sam?
Are there any more questions?
Yeah. Well, I think the answer to that question is yes. But what's wrong with that? What's wrong with having 5 miles of a grid and then 5 miles of nothing and 10 miles of a grid?
I'd probably more than 5 miles.
Yeah. But I see nothing wrong in that, and that's part of the principle enshrined in Network Rail's managed track position standard, published in 2019.
But would not have to adhere to an overall structure, so the bits would connect together.
I don't think that's absolutely essential. For example, any major layout renewal, switch and crossing layout renewal, big double junction somewhere, that should all be fixed.
Totally agree.
With an external survey grid that is maintained.
Totally agree.
There's another question here. I know you were trying to. Sorry, I don't know your name.
Andrew Skinner. Thanks very much, Richard. I'm sitting here as a TNRS engineer, so that's really enlightened me this evening, and to have that history lesson as well as bringing us up to date is fantastic. So thanks very much. Could I just pick up on the little teaser that you left us with at the end? What simply is the reason not for using the available data after track maintenance rather than renewals? Is it time cost or not the need for quality? or some other
I
route?
perceive not the need. I perceive not the need. Malcolm, can you help?
Sorry, no,
So would you suggest it's maybe akin to, if I look at a traction and rolling stock example, we might have an overhaul specification where parameters are quite tight, whereas during routine maintenance between overhauls, maybe our parameters are a little looser. Is it that sort of parallel?
I think so, and I think it's also got a lot to do with Network Rail's budget and the fact that it's in 5-year cycles and nobody thinks long term. Network Rail's track policy for 2005, sorry, no, for 2013, CP5.
Yeah.
Sorry, CP5 document mentions whole life cost 200 times. It was flavour of the month, and it's gone away again. Whole life cost means you invest initially to reduce the long-term maintenance cost, and after 100 years, it's been cheaper. We don't do that. Like the Americans, we follow the Americans. The Americans don't do it either.
So it's just the short-term view.
I think so. I think so. There's a lot of pressure on maintenance budgets, so therefore we're not going to do the extra this or the extra that.
Which is a problem. Thanks very much.
Okay, thank you very much. Rodney.
A point to interest Andrew as a fleet engineer, or whatever you now call on the Great Western. About 1985, I'm guessing, I was asked by the divisional manager of Reading here, well, why can't the Western run faster? Now, we'd obviously got 125 mile an hour trains there, but I looked quickly at the state of the Great Western Brunel's route and came to the conclusion we could actually obtain the geometry in terms of cant primarily and transitions very easily to run at 140 miles an hour. But it's never been pursued. And if the one reason is level crossings, well, we could actually run at 140 from Acton through to Dicker and Wantage onto wherever, Bath pretty well, certainly Chippenham. But nobody seems to have pursued the idea, Andrew, of going faster with your 800s.
I did hear that I did hear that this concept that you've described has been looked at on the eastern region between York and Darlington, known as the racetrack.
I do recall one instance at Kilburn where we had to shoot a 90 mile an hour TSR. The line speed had increased to 110, but it didn't help when the rolling stock just kept going past the risk signals because the signalling hadn't been adjusted to suit the line speed. So you've got to look at the whole setup.
There was a lot of work done on the West Coast in terms of signal sighting and also warning boards. We had a big argument about how many differential speeds can you have on one warning board. The rule was 3.
Yes.
And of course, the difficulty we had on West Coast is that the tilt mechanism on the Pendolino was not the same as the tilt mechanism on the Voyager. Voyager's was hydraulic and the Pendolino's is electronic. Pendolino tilted more than the Voyager. But we also had a risk with Pendolino of overturning. A number of tilting trains have overturned in the world. So you take the design rules for track to their limit against the potential overturn with a tilting train. You then have to allow for the 1 in 100 years gust of wind and side loading. So I think there was some work done, certainly up in Cumbria, possibly over Beta, but I think certainly over Cumbria, as to whether or not the speed, the potential speed that could be allowed had to be reduced to mitigate against the risk of overturning or becoming close to overturning. Because of course, if you track defects that are acceptable to the track engineer, push the safety limit the other way when it comes to train.
Good. Have we got any more questions from the room? Okay.
Right,
I think.
I've got two comments. They're not questions online, but I will very briefly say David Marquis, sorry, getting the presentation. Brilliant presentation, very interesting. Thanks very much. And I've also got a great presentation. Thanks for having me from the Welsh PWI section from Nathan Butts over in Wales. And two more great presentations which just popped up as well. So lots of well done. Thank you from online. Okay. Nick.
And just an update which should warm Richard's heart. The MSAT machines, which had stood idle for a long time, are actually being refurbished, including the one with a nameplate on the side which actually says Richard Spoors.
I was going to mention that.
Oh, well, that's two people in the room with names on trains then, yeah. Malcolm. At which point, since you had a starring part in the talk, Malcolm, could I call on you to do the vote of thanks, please?
You want me to go up to the front? Or
well, if you can come down a bit, they might be able to hear you on the microphone.
Now, it's a great pleasure to me tonight to be able to propose the vote of thanks. I did invite Richard to come to do the talk tonight because I've known him for, we better say, many decades, haven't we? Multiple decades, yes, it is. But I knew we were going to get not just a history lesson, but we were going to get a lesson which is the development of what has happened since machines first came into the UK, and I remember that very well, and right up to what is being done at the present time. And that development was very largely done in British rail days. I think, to a large extent, apart from the work that you did, Richard, in rail track days and then beyond rail track, there hasn't been too much more development from what was there in the early 1990s. All the technology that was used at that time is still being used now. The improvement has been in what PASA and the TISA, for that matter, have put into their machines to enable us to use all the equipment and technology that's available to us. There are two or three things I'd like to just say to it. There was a mention about this 140 miles an hour. It isn't just level crossing, you bear in mind. But the rule book always said to us that if it was speeds higher than 125 miles an hour, you couldn't do patrolling and so on. But we always were, traditionally, they were still in place and have been until very recent times. So if you were above 125 miles an hour, you could not patrol normally in the week in the way that it was set up to do. I think that's right.
You're correct. Yeah, you're right.
So that was one of the main reasons for it. I'll go back to the West Coast Main Line, and as I know that fairly well, probably not everyone knows, unless you've actually worked on it, but between about the 3 mile post at Kensal Green and the 58 mile post of road, you've got a railway that is 6 foot spacing all the way across. You do not have a wide space between the fast and the slow lines, so that when you get junctions like Hanslope, for instance, which I maintained for many years, you have through bearers or timbers or bearers between the two fast lines, and then between the two middle lines, the up fast and the down slow, of course. So trying to be able to maintain that with 2 lines always open for traffic is very difficult, and that's the sort of thing that was developed by putting 2 machines together in harness to be able to do the full crossovers and also take a middle line possession and do the across the 6 foot across the space between the fast and the slow lines. I'll just go back to one other thing as well, because this is the sort of thing that Richard has done through his career. You've seen that there's been a lot of things developed, and he's been at the forefront of it. We all know that he was at the forefront of it. Now, he's also been in extremely senior positions in his railway career, but he's never forgotten his roots. was ever there was anything that needed to be developed. It didn't matter where he was or how otherwise engaged he was with things. He was always able to take on board things like developing the way that we do our surveys, the way that we maintain our track, the way we use all the information that we collect, and be able to use that to maintain our track effectively. Now, back in 1985, and I remember this one because at the time he was divisional engineer at Nottingham, and between about 1978 and that time, there'd been a lot of development led to a large extent on Nottingham Division, and I had followed it while I was at Watford on the control of machinery in general with lasers. So we decided that our divisional engineer at the time, it was Jeff Queen, said to me, I was a renewals engineer at the time, right, we should do the first 100-mile-an-hour opening after ballast leaking work over the weekend, but we just used the standard possessions to do it. He was like that, which is a good thing to be able to do. We didn't take a week and shut the whole railway and that sort of thing. We did it in the normal possession times. Now, the thing was about Nottingham at that particular time, they had the first DTS, which was not self-propelled. It was towed behind an 07 tamping machine. And I borrowed that for the weekend to be able to work with one of our 07 tampers and a DTS. And we went in on the Saturday night as normal, did 500 yards of ballast cleaning on the down fast line, opened the line at 40 miles an hour on the Sunday afternoon at 3:50, which is the usual time, and we took possession again at just after midnight on the Monday morning, and at 6 o'clock in the morning we took it off to 100 miles an hour. We'd used the DTS during that particular time. Now, all those developments were not just the fact that, oh, well, headquarters was dealing with it and so on. It was led on the divisions very much. Richard was at the forefront of that, because anything he wanted to do, things got supplied. He had the nod from various people because he could persuade them properly and technically this is the way we should be going. And there's an awful lot of people being grateful for that. We've had a good history lesson tonight. It's not just a history lesson, it is the development of what's happened on our railways for the last 50 years or so, up to privatisation. Anyway, thank you very much, Richard, for coming tonight. I'm very grateful for you coming. Please join me in thanking him in the usual way.
Thank you, Malcolm. Okay, next meeting. Mick, do you want to announce your next meetings?
Yeah, just a quickie, because it's quite important. We've actually changed meetings. Our next meeting was originally going to be the fast charge battery train between West Ealing and Greenford. For reasons which you probably already know, we decided perhaps it's a bit risky to do that one at the moment, so we've swapped it. So our next meeting, which is on Monday the 6th of February, it's at Swindon, and that will be the TFW, Transport for Wales, Rolling Stock Strategy by Andrew Gainsbury. That's at Weston House, Swindon, 5 o'clock. Everybody welcome. And the talk that would have been that day, the fast charge battery train, that's moved back to the April slot that Andrew was originally going to be, which is Monday the 24th of April, by which time we hope the train will actually be there. Thank you.
Okay, Richard?
The next meeting is the 1st of February, probably, rather than the 8th of February, Wednesday anyway, in this room again. It promises to be a most interesting meeting, but we're not quite sure what it's going to be yet.
Okay, don't think there's anything else, is there?
No, nothing else to say.
All that leaves me to say is thank you for everyone for coming along. Thank you for our visitors from the IMechE. Thank you for making the effort joining us this evening. And lastly, many thanks to Richard for a very informative and outstanding talk this evening. So thank you very much for that. Thank you for the people online for joining in. I think we've still got a couple of people left. Thank you for your participation, and we shall look forward to the next thrilling episode. Thank you very much, and that concludes the meeting for this evening.
Thank you.
Just to say the laptop camera did work fine.
Say again, Ray?
The laptop camera worked fine.
There's too much noise. Hang on.
Say that again?
The laptop camera was fine. Look, the
There's too much noise around here.
So I need to apologise to him for not phoning him back. We can have a chat. So I was hoping he'd be here tonight. Just need to chat in person.
You're still there, Ray?
yeah, still here. Can you hear me?
I can. You went
Yeah,
all in.
just say that your laptop camera worked fine.
It wasn't the laptop in the end, it was Phil.
Oh, okay.
Connected on his machine.
But it did work.
Yeah. Good. Okay.
Brilliant.
Thanks.
Thanks very much.
Okay.
Cheers.
I couldn't see the picture on here.
I could happily see that one. I could see the presentation I was showing from here, and on this one I could see